With falling pressure, there will be rain in the next few days. When meteorologists make statements like that, they are very often, contrary to popular belief, quite right. They know that low pressure on the ground means clouds are forming at higher atmospheric levels. These clouds then produce rain. All this can be read off from a barometer. The man who first realized this lived during the tumultuous time of the 30 Years' War, more than 350 years ago. He was the mathematician, philosopher and scholar Blaise Pascal. Pascal was born in Clermont-Ferrand in the Auvergne on the 19th of June 1623. Soon, however, his family moved to Paris. His father, Etienne Pascal, took his children's education into his own hands. At first, he only taught Pascal Latin and Greek grammar. He wanted to wait until Pascal was 15 before teaching him the languages themselves, the sciences, or even mathematics. He removed all mathematical books from their house. Despite this, Pascal taught himself the foundations of geometry when he was only 12 years old. It was only after some time that his surprised father noticed Pascal had skipped several levels of his education. He then allowed Pascal to read a book by the Greek mathematician Euclid. Pascal proved to be a child prodigy. At 15, he took part in meetings with leading mathematicians organized by the Minim friar Marine Mersenne in his monastery cell. Amongst them was one of the most famous mathematicians and philosophers of his time, René Descartes. When Descartes was presented with a treatise by Pascal on conic sections, he strongly wanted to meet its author. At first, Descartes could not believe it had been written by an adolescent. In 1639, Pascal and his family moved to Rouen, and at 19, Pascal tried out his talents as an inventor for the first time. He wanted to make his father's work as a tax collector easier, and so he invented a calculator. The Pascaline was a mechanical calculator capable of addition and subtraction. There were 10 dials moved by cogwheels, each of which had 2 rows of numbers fixed to it. With the help of a pen, numbers could be entered on the dials. To add 5 and 7 together, for example, the 5 would be entered on the dial, which would then need to be turned by 7 digits. If a dial was turned further than to number 9, a hook would engage the neighbouring tens dial and turn it 1 digit further. Then the sum 12 had only to be read off from the display. Pascal worked to improve his invention for 10 years. He also tried to sell the machine, but none of the 50 calculators he built worked reliably. It was not possible to produce cogwheels with the required accuracy at the end of the 30 Years' War. The components of the complicated machine kept jamming, and to repair it, the whole machine needed to be taken apart. It was the beginning of the end of Pascal's entrepreneurial career. He even advertised his calculator to the Swedish Queen Christina, but without success. However, the machine was to be the model for many later mechanical calculators. In 1646, 23-year-old Blaise Pascal and his sister became deeply religious. They converted to Jansenism, a Catholic movement of the Counter-Reformation. In the following year, Pascal suffered a serious paralysis. In addition, he was plagued by constant pain. His inquiring spirit, however, remained unbroken, and one area appeared to be particularly worthwhile to him, that of atmospheric pressure. He was especially taken with an invention by the Italian Evangelista Torricelli, the barometer. For better understanding, he recreated this barometer with the help of his father. Pascal completely filled a 1-meter glass tube, open at one end, with mercury. Then he dunked the open end into a vessel which also contained mercury, and noted that the liquid mercury flowed out of the tube, but only some of it. Most of the mercury remained in the tube. The level only ever dropped to around 76 centimeters. Something was preventing the complete draining of the glass tube. The explanation. The weight of the air above the container, right up to the edge of the atmosphere, pressed down on the mercury outside the tube, thus preventing the liquid in the tube from escaping. Regardless of the tube's dimensions, the mercury always dropped to a height of 76 centimeters. This was due to the properties of pressure. A certain amount of pressure acts on a given surface area because of the atmospheric column of air. Exactly the same counterpressure acts on the same area when the mercury column has a height of 76 centimeters. To prove his explanation, Pascal asked his brother-in-law to take the filled tube and climb the Puy de Dôme, the highest volcano of the Massif Central near Pascal's place of birth. According to Pascal's theory, the air column would have to be a bit shorter on the summit of the mountain, so the atmospheric pressure should be a bit lower than in the valley. Therefore, the mercury column would have to move down, because less air would be pressing on the mercury in the container. The result of the experiment confirmed Pascal's assumption. The mercury column was around 1 centimeter lower on the peak than it had been in the valley. Pascal recognized that the height difference of two locations could be measured with the help of a barometer. He also discovered the possibility of forecasting the weather with this instrument. If any changes to the atmospheric pressure took place because of the approach of a high pressure area, then the instrument would react. When the atmospheric pressure rose, the mercury column in the barometer rose as well. If the mercury column sank again, an observer would know that a low pressure area was approaching. Accordingly, bad weather could then be predicted. In 1653, Pascal summarized all the results of his examinations in a treatise entitled The Equilibrium of Liquids and the Weight of the Mass of the Air. Now others were able to put his findings into practice. Pascal himself was only interested in the theory. The experiences with his calculator were a warning to him. Today, a barometer can be found in every weather station. There are fluid-based barometers that are still mostly filled with mercury, just like Pascal's instrument. And there are aneroid barometers. Here, a hollow body made of a very thin metal sheet is deformed strongly or weakly depending on the atmospheric pressure. Aviation also puts Pascal's musings into practice. Altimeters in aeroplanes are basically barometers too. They measure atmospheric pressure, calculate the altitude from this figure, and then display it. Pascal also occupied himself with the pressure conditions in liquids. He recognized the principle of the communicating tubes, according to which the liquid in the connected containers finds the same level in each. The water supply of our cities also works on this principle. The domestic tap and a water tower are communicating tubes. The pressure in the water pipe arises because the higher water level in the tower is trying to equalize the uneven level. Even hydraulic jacks work on this principle discovered by Pascal. Liquids hardly deform at all under pressure. Instead, they pass it on. In a jack, hydraulic oil is pressed into a cylinder with the help of a lever. The oil transfers this pressure onto a disc of a much greater diameter. Through its larger area, the disc is able to exert much more force. However, it moves a smaller distance than the lever does. If the smaller cylinder is pumped often enough, the effect is enormous. A car weighing more than a ton can be lifted by a lever operated by muscle power alone. All hydraulic devices work on this principle. With its help, large forces can be produced with minimal effort. A long stroke in the hydraulic cylinder produces a great force in return. After the publication of his treatise on atmospheric pressure and the theories concerning pressure in liquids, Pascal was increasingly drawn to the monastery of Port-Royal. He allegedly tortured himself with a thorned belt, and he questioned the role of mankind in the universe. In the monastery, he became a religious philosopher. Pascal placed faith above reason, since, according to Pascal, faith could grasp things that were hidden from reason. In 1662, Blaise Pascal died at only 39 years of age. In the current climate of belief, it is not Pascal the philosopher, but Pascal the scientist who is more prominent. When an international commission in Paris reclassified the system of physical units in 1960, the label chosen for the measurement of pressure was the Pascal. Meteorologists all around the world use this unit for atmospheric pressure. Air exerts a pressure on the Earth's surface of 101,300 Newton per square meter. This corresponds to 101,300 pascals. Since this is a somewhat unmanageable number, it is usually reduced by a factor of 100 and stated in hectopascals instead. Under normal conditions, atmospheric pressure is approximately 1,013 hectopascals. How much we humans are dependent on atmospheric pressure is demonstrated by passenger aeroplanes at high altitude. Here, the atmospheric pressure is much lower than on the ground, too low for the passengers. For this reason, passenger jets have specially constructed cabins to maintain an artificial atmospheric pressure on board, which is close to the atmospheric pressure on the ground. Enormous water pressure acts on submarines when they submerge. They can only withstand this pressure through special designs, adapted to the pressure conditions. Pascal's insights into the pressure conditions in liquids pointed the way. Science, mathematics and philosophy. Blaise Pascal was a leading scholar of his time in all these areas. What else would he have discovered had his life lasted longer than just 39 years?